Hello everyone, my name is Jiang Qijun. Today I will represent the latest paper, NeRV360, published by the NHK Science and Technology Research Laboratories in Japan. So this paper explores how to use neural video representation to resolve computational bottlenecks in 360-degree video compression. The visual reality application. 360-degree videos require ultra-high resolution of 6K or more to maintain the visual quality of local viewports. This creates significant data transmission pressure. Recently, neural representation for videos, or NeRV, have shown immense compression potential. However, existing NeRV architecture lacks scalability when processing ultra-high resolution. They face several GPU memory consumption and decoding delay, failing to meet the demand of real-time streaming. So what is scalability? When scaling the resolution from Full HD to 6K or 8K, if you only want to see the Full HD viewport in front of you, traditional NeRV cannot decode just that specific area. The GPU must first completely render the entire 6K canvas in the VRAM and crop out the Full HD section the viewer wants to see. The pixel count spikes instantly during decoding, accompanied by extremely high computational latency. So please look at the part A. This is the traditional decoding pipeline. Traditional architecture must completely decode the entire 6K panoramic frame in the pixel space before performing perspective projection to extract the current viewport. And this decode full panorama first and crop later mechanism forces the system to consume massive computing power to reconstruct non-visible area that VR headset will never display. And this makes real-time rendering impossible. And then please look at the part B. To eliminate this computational redundancy, the core of this paper is moving viewport extraction from the pixel space forward to the embedding place. After receiving the viewport parameters, the system crops out the required area directly within the low-dimensional feature map, and only send this local feature to the backend decoder. This end-to-end architecture avoids reconstructing panoramic pixels, significantly reducing computational complexity and hardware requirements. So this is the system architecture. This is the core of how NeRV360 achieved a 7-fold reduction in memory load. It is divided into 3 stages, which the corresponding feature dimension changes show below. The left side is the encoder. The high-resolution panoramic image undergoes a 4-stage downsampling. The spatial dimension is highly compressed to 1 in 24, and the number of channels is reduced to the base level D, forming an extremely lightweight latent feature YT. And by the way, VP stands for viewport. It has already been cropped via perspective projection. And T means time, a specific time point in the video. And theta means the longitude of the user's viewing direction. And phi means the latitude of the user's viewing direction. And the red part, viewport extraction in the middle, is the main focus of this paper. After receiving this lightweight feature, the system does not decode it yet. Instead, it first performs channel expansion, increasing the dimension from B to C2. This prevents the loss of high-frequency detail caused by subsequent bilinear interpolation. Then it applies perspective projection to crop out the local feature matching the viewport directly in the latent space. And by the way, let's talk about the bilinear interpolation. When calculating new pixel values, this algorithm takes the weighted average of the 4 surrounding original pixel, resulting the smoothing. If performed directly in a low-dimensional feature space with very few channels, this blurring effect is magnified. Finally, the decoder only need to perform upsampling and color reconstruction on this local feature. This solves the computing power issue and makes real-time decoding possible. Alright, let's move to the module. The upper part is the viewport decoder, which constructs low-dimensional feature into high-quality pixels. The lower right is the STAT module, providing the control mechanism from viewport chains. The decoder stakes multiple SNERV plus STAT residual blocks. Then take the local feature YVP, gradually upscale the resolution, inject a spatial temporal condition, and output the final viewport image XVP. Unlike traditional NeRV that relies slowly on time t, NeRV360 depend heavily on the viewport. As shown on the bottom left, the combined time p, longitude theta, and latitude phi, and MLP fuses this into a joint embedding factor Z. Factor Z then enter the STAT module. The network dynamically learn a scaling factor gamma and a translate factor beta. It then linearly modulates the main feature f using gamma times f plus beta. This enables the decoder to seamlessly handle viewpoint shift and image deformation. Okay, so for performance evolution, with all models fixed at 2.2 M, NeRV360 achieved a major breakthrough. Let's see the figure down below. The vertical axis is dynamic viewport PSNR, and the horizontal axis is decoding speed, that is FPS. So its decoding speed is 38.4 FPS. It's 2.5 times faster than NeRV, successfully achieving real-time processing. Additionally, the bubble size indicates a massive seven-fold reduction in GPU memory, while the Viewport PSNR remain highly competitive. competitive. Okay, so architectural optimization significantly lower training cost. Training a 6K model used to need over 50 GB of industrial VRAM. NeRV360 cut this to 21.2 GB, making it viable for consumer-grade GPUs. Ablation study confirmed three key points. First, feature resolution outweighed channel count for image quality. Second, channel expansion must precede interpolation to keep high frequency details. And third, spatial coordinate in the STAT module are essential for accurate reconstruction. Okay, let's move to implementation. Since NeRV360 is an open source, so I implemented DCVCHEM360 and architecture optimized for 360-degree videos provided by my professor. This terminal screenshot shows the decoding process. We can verify two main results. First, the decoder successfully parses the header info, including frame count, resolution, and projection parameter. And second, with GPU acceleration, decoding takes only 3.45 seconds per frame on average. Okay, let's see the output. You can see two figures down below, test video and decode video. The decoding output shows structured strip instead of standard color image. This happened because the model operates in the feature domain. The neural network uses convolutions to compress spatial detail into a high-dimensional latent space. As you can see, the decode video is not just a normal image. So this strip are simply feature tensor before the final color reconstruction. This visually confirms the model's ability to extract and compress deep constructural information. So this is the final conclusion. These two architectures present the major schools of neural video compression. NeRV uses implicit representation. It lacks generalization because it memorizes a single video into its weight. Changing videos requires hours of retraining, making it unsuitable for live streaming. However, by shifting heavy computational cost to offline server training, it allows VR headset to decode viewport with extremely low power and high speed. In contrast, DCVC uses a hybrid architecture. Instead of memorizing. It learned general rules like optical flow and residuals. This strong generalization allows it to compress new videos instantly, making DCBC ideal for real-time live streaming scenarios. So this is my final report. Thank you for your listening.